Welcome back to this series of videos in which we are doing the precipitation exercise. In this video we're going to solve exercise 4 about areal precipitation using the hypsometric curve. The notebooks for this exercise are, as always, in folder notebooks, and exercise 4 you have the complete version and the incomplete version. One is blank in the code cells and the other one is not, so you can try to solve it, and in case you have any problems you can just check it from here. I'm not gonna use the incomplete, but I'm just gonna start with a new Python file or notebook. To do that, just click plus and then Python 3, and we created a new notebook. I'm gonna delete this one that I don't know why it's there. Good. And then remember, change the name, and we're gonna call it exercise 4 solution. Yes, okay, so exercise 4. I have to warn you that this exercise is a little bit different from the one that I gave you in the class. Both have the same goal, which is calculating the mean annual area precipitation for a catchment, but the one in this video is more developed and is applied to a real case here in Cantabria. So this is a little bit more complicated than that one that I gave in the class, but what I'm showing you here is more than enough to solve the other exercise. The purpose of the exercise is to calculate the mean annual precipitation in a whole catchment. For doing that, I give you 3 files. One is a raster, that's a map of the elevation of the catchment called the digital elevation model of the catchment pass here in Cantabria. Then I give you the rainfall daily series for that catchment, for a series of gauges that are in that catchment, and apart from that, the location of that catchment, of that gauges are in another file. Well, first of all, as usual, let's start by importing packages. Import numpy as numpy, import pandas as pd, etc. There's something, let's save some time. We can just do this. We can delete here and drag and drop. This is very useful, and now we have all the packages we need here. So it's numpy, pandas, regular. These 2 lines are because some plots are gonna show us some warnings, so just to skip those warnings, and then the regular matplotlib with the seaborn style. Good. And like this, we again have only one window. Areal precipitation. The areal precipitation is the aggregate value of precipitation that applies to a catchment. It means that instead of one point value, which are gauges, we have a value that is extended for an area. That's the areal precipitation. To calculate areal precipitation, we use a formula that is very similar to the one that we used in exercise 1, which was the interpolation of precipitation. The formula is the summation of a weight by the value of the precipitation in one catchment. There are different methods, and those methods differ in the way we calculate weights. We're going to use the hypsometric method. There are more simple methods like the mean. In that case, the weights will be 1 divided by z, the number of gauges. But we're going to use the hypsometric method to introduce the idea that the higher in the catchment, the higher the precipitation. The steps we need to take to solve this exercise are 3. First, we have to fit the hypsometric curve for our catchment and calculate with that hypsometric curve the weights. That means the vector of wz. Second, we have to estimate precipitation for each of the elevation bands in the hypsometric curve. With that, we will get p and p set. And the third will be just to compute the summation of weights by precipitation. So the first step is the hypsometric curve. The hypsometric curve defines the fraction of a catchment that lies below a specific altitude. For instance, let's say we have a catchment with like the pass here, and we want to know how much of the catchment is below 500 meters. So the plot will give this value for every single location. It's easier if we start working and then we see the plot, and then you'll understand what's the hypsometric curve. Good. Control 2 times M, and you convert this into a markdown, and let's give it a title. So first step was the hypsometric curve. Good. To compute the hypsometric curve, we need to import the digital elevation model, the DEM. I provide you with, remember we are here in data, you have this file here, which is the digital elevation model for the past catchment. And this looks like this. I'm gonna open it with other software, that's gonna be easier to watch. So this is data and then pass. This is what is inside the file. So a nasty file, which is a way that many GIS programs save maps, consists on 6 rows with the attributes of the map. These attributes include the number of columns, number of rows, the X coordinate of the lower left corner, the Y coordinate of the lower left corner, the size of each of the cells in the map, and then a value that is a code for no data, meaning that each of these -999.000 represents a value that has no data. And then here we have the values with the cells with data. To import this, I have a function developed that I give you in a notebook. So if you go to here, notebooks, you'll see there is one called functions precipitation. In this notebook, I just put it all together, all the functions that we're using through these exercises. You see the linear regression in exercise 2, this is from exercise 5, etc., etc. And here there's a function called read ASCII. We're gonna use this to read the digital elevation model. So to import functions from other notebooks, we're gonna use a magic function. These are called, every time you see this symbol with run, load, whatever, it's a magic function in Python. With this, we can just run the whole functions precipitation notebook. So I'm running all of this inside this notebook. And with that, we already have a function called read ASCII. You see, now we have the function. What do we need to input this function? Remember that the help, I define the help here with all these red letter code, and this is what it's given here when I press Shift Tab to ask for help. So I need the file name. Remember, 2 dots to go 1 folder up. Then we get into the data folder, and the file we want is dem of the past river. Good. And we don't need to input anything else. So the output are 2 things. One is the map, and the other one is the attribute. If we go to this here, so one is the map, this matrix here, and the other one are these 6 values here. Let's save it as DEM and attributes. Good. And we can check the attributes, for instance. The attributes, which are 139. Yep. Good. So this we see 139 columns, 230. So these are properly read. Good. And let's check what's inside them. Them is just an array of 2 dimensions. If we call shape, we can see the dimensions, which are the number of rows by the number of columns. These 2 values should be the same as here. Let's plot the map, and we can see what's inside. Plot the DEM. plot a DEM, we're gonna use this function in matplotlib, which is called imshow. We just put the DEM, and then we're gonna give a color map, which is cmap, and I like this one, for instance, pink. Okay, so this is the DEM. We can see the rivers. This is the lower altitude. This is the higher altitude. Let's make this plot a little bit better. So if we call this image, IM for image, we can create a color bar like this, in which we can see that the elevation applied to each of the colors in the map. So it's just like a legend. And then to the color bar, which is CV, we can give it a label, meters above sea level. And let's skip this axis here to make the plot clearer. We do that with PLT axis off. And then remember the semicolon just to avoid any inconvenient print in there. So now we have the map. This is our map. So the lower elevation is 0. Here the higher elevation are around 1600, which are around here. Okay, good. If we want to ask, for instance, minimum and maximums of the map, we can just call numpy nummin dem numpy nan max dem. This none is required because we have not missing values in them. If we go here and we just plot them, we see that there are plenty of missing values. This is obviously because all this white data or white cells are missing. So in case we want to go to ask for a minimum, maximum, or the mean, we need to ask the none function. This just deletes all the missing values and calculates the mean of those values that are not missing. So minimum value is 0 elevation, maximum value is almost 1,700 meters above sea level. Good. So now let's derive the hypsometric curve. Okay. First of all, we have to define some elevation thresholds. That's the divisions in which we are going to divide the catchment. So to do that, we're going to use the numpy arrange function. We have to provide a start value, which is 0, the one, so the lower elevation, an end value or stop value, which is going to be higher than this, for instance, so 1,701. I'll show you why it has to be 1, and then a step. So we're going to create deviations every 100 meters. If we plot this, so we create a series between the start 0 and the end 1,701 every 100 meters. I need a 1 here because otherwise this would have stopped in 1600, and we need to go further to include all the cells in the map. So that's why I need here a 1. And then let's start by calculating the number of cells in the catchment. Good. We need to call, okay, to do that, we need to use a function that is called isNone, and this is going to tell us if the DEM has a missing value or not. If this is true, it means that this is a missing value, and if it's false, it means that we actually have a number for that cell. If we put the tilde here, this makes the opposite of that selection. So now we have trues for cells with values, and we have false for cells with no values or with missing values. Python understands that false is a 0 and true is a 1. So if we create the sum of this, we have the number of cells with values in the whole catchment. And let's save this number of cells. Okay. And now let's start creating the hypsometric curve, and let's start with just one example for elevation 100 meters, and then we'll make a loop to calculate all the elevations. Okay, so we set a threshold, and in this case set is going to be 100, and we need to calculate number of cells below the threshold. Number of cells below the threshold. So we're gonna do something very similar to here. First of all, we're gonna do this. So dem is lower than set. Okay, so now we can get a map of false and true. It will be true if the value of the map is below set, which now is 100, and it will be false if it's above or is a missing value. If we just sum this, remember that false is 0 and true is 1. This is the number of cells below 100 meters. Let's save this. We have a warning here, meaning that we're trying to sum missing values, but we can just skip it. So the value in the mesh hypsometric curve, remember the symmetric curve is the fraction of the catchment below a specific elevation. So it will be the quotient of this n by the number of cells. So in the case of 100 meters, will be n divided by 100 cells. This means that almost 60% of the catchment is below 100 meters. Okay. This was just an example for one elevation band. We have to repeat this for all these elevation thresholds. How do we do that? With a loop. Loop for all elevation thresholds. Good. Let's create a table to save the data. Okay. And we're gonna call it ipso to create, well, this is gonna be a series actually. So pandas series, remember that this is a table with only one column. So pandas is something similar to Excel. We're working with tables. If it's a pandas data frame, this means that I have several columns. If it's a panda series, it only has one column. And as the index, we're gonna put the elevation. So ipso looks like this. Okay, for each elevation, we have no data so far. So let's compute the hypsometric curve. So we're gonna repeat all these steps for every set. So for set in all the elevations, remember that set S is all these 0, 100, 200, etc., etc. We're gonna calculate this here divided by the number of cells, and this is gonna be saved in ipso set. Okay. Now we can see that we filled the data here. Good. Let's plot the isometric curve. We just need to plot set S, again ipso, and this is our curve. Okay. To make this a little bit nicer, we can put a title, hypsometric curve, and we can plot X label elevation in meters above sea level, and Y label, which is the area or the fraction of the area. This has no units. Semicolon to avoid this line here, and now we have our hypsometric curve. So with this plot, I can better explain what's the hypsometric curve. We can go to any elevation we want, for instance 1000, and ask how much of the catchment is below this elevation. So we just go up here, then here, and this means that probably it will be something like 95% of the catchment is below 1000 meters. From this, we're gonna calculate the weights, which is the end of the first phase. Well, to calculate the weights, we're gonna create two lists. Remember that a list is our brackets, so this is an empty list, and then another list that I'm gonna call weights, which is also empty, and I'm gonna fill these weights. Important, remember that we have something that is set S, okay? So we have some thresholds from 0, 100, and 100 to 100. I'm gonna calculate the mean value for each of these pairs, and this will be the representative value for each of the elevation bands. To do that, I'm gonna do something like this. Cj in -1 okay, and I want you to understand what I'm doing here. Print I set j. Okay, so the first time I enter the loop, I'm gonna read the first and the second value in the list. The second time that I enter the loop, I'm gonna read the second and the third value, etc., etc. If I calculate the mean of this, numpy mean, this will be the representative elevation. I did something wrong here. Up, this is wrong here. So this will be the representative elevation for each of the elevation bands. So the first band is between 0 and 100, so just take the mean value, which is 50, as the representative value. The second band was from 100 to 200, so representative value is 150. Okay. To save this into the previous list set bands, so I'll just put this set bands, and then I append. This means that every time that I give a new value here, this will be appended, meaning added to this list here. If we do just this, we can see that now set bands, it's filled. Okay, let's merge these two. So just select both of them and then Shift M, and this is merged. Good. So now I created the set bands, and I want to create the weights. The weight is simply the difference. Imagine we are between two values. This is not what we're doing right now, but between 0 and 250. So the weight used for the areal precipitation is the value of the hypsometric curve in this upper bound minus the value in the lower bound. So in our case, this will be hypso. The upper bound will be set j. The lower bound will be hypso set I. Okay. And then we can just append these to weights. So weights append. Okay, and now we can see that weights has values. So these are the weights for each of the elevation bands. Let's save all these in a panda series that we're gonna call weights. Also, so PD series, and we're gonna provide some data. The data is gonna be weights, and the index is gonna be the set bands. Now you'll understand why I'm calculating the set bands and the weights separately. So now we have a series for each of these values, 50, 150. This is elevation. We have the weight. This is the first step in the calculation of the areal precipitation. We can plot the weights similar to how we did the hypsometric curve, and we can improve a little bit the plot by giving an X label, which is again the elevation in meters above sea level, and a y-axis, which will be the weight, and this has no units. Remember, semi column, And this is the end of the first part of the exercise. The second part will be to estimate precipitation for each elevation band. I call it precipitation versus elevation. Let's start by importing data. Good. The data is always data, and it's daily precipitation for the Pass River here. So pandas read CSV and 2 dots to go one further up, data and daily precipitation pass. This is a CSV file, and let's see if this is good enough. Okay, so we have several stations and we have a date here. Let's convert these to dates. To do that, we can use this attribute, which is parse dates true. Now this is not a string, or it will not be a string, it will be date. And let's convert this column into the index. Index call equals to the first one, which is 0. Okay, now this is okay. Let's save the data as precipitation daily, and we can just plot, for instance, the last 5 rows with the tail function. Good. And also we have to import the attributes for the station, meaning this what is the location and elevation of each of these stations. This is given in stations underscore parse here. Okay, so PD read a CSV file, data stations pass dot CSV. Well, let's convert code into the index, and to do that we can say index call equals code. Now this is okay, and we're gonna save these stations. Call it like this to be short. Good. With this data, we need to, first of all, we are interested in in mean annual precipitation, and the input values are daily annual precipitation, daily precipitation. So we have to convert the daily series into an annual series. So let's convert. Let's create a mean annual precipitation at the stations. Good. I'm gonna start with example for station 1115. So station is going to be 1115, and let's plot the data we have. We're gonna plot PD, the index, which is the date, against PD station, and to make it clearer, we're gonna give a narrow line width, something like 0.1. Okay, let's improve a little bit this plot by PLT figure. We already seen this in another exercise, and give a size to the plot. So 15 by 3.5, and also let's give it a Y label. Label precipitation, which is in millimeters, semicolon, and this is our. So from this daily series, we need to create an annual series, and we can see that there are some gaps in the series that we have to eliminate. What is the simplest way to create the annual series? So we call our data, which is precipitation daily for our station, and we use a function which is called group by. This is going to make groups out of our data, and we have to tell which is the classification we want. So in our case, we want to classificate the same value, okay, the same series, sorry. From its index, we're going to extract the year. So we're going to create groups, and each group is a year. And then we don't see anything from here, but we can apply functions to each of those groups. If we apply the mean, now I created for each of the groups, which are the years, the mean value. Okay, there are plenty of missing values. That means that there was not a single date with data for those years. Just see here that the plot starts at 1961, probably is this one, and ends in 1991, which is probably this one. Okay, so the rest of is just missing data. We can save this as precipitation annual, plot it to be a little bit easier to see. So annual, you see, okay, so we have data from 1961 to 1991. There are some years with peculiar low precipitation. Why could that be? Okay, this is probably because there's a lot of missing data here. So you see that this gap is here is 1965, 1967, 8, etc. And it is exactly the years with lower precipitation. So we're gonna get rid of some of these years. Let's calculate the days per year. We're gonna use something very similar to this, so we can just copy. But instead of passing the mean function, we're gonna pass the count function. This function counts the number of days with data in each of the years. And let's directly plot it. So days per year. Okay, if we put here a semicolon, we avoid that line. So we see that for many years we have not a single data, and some years we have very little data. So basically we're gonna set a threshold in the numbers of days per year, and we're gonna use just these few values to calculate the mean annual precipitation in this station. Let's set a threshold, so we're gonna get rid of all the years with less than 330 days with data. Okay, so now for instance, if we say days here, which is what we just created, and we ask for years with less than 330 days with data, we can only get this, so we're gonna keep these years here. Okay, we can pass this as a lock into our series, so we have this series of annual precipitation, and we can just ask for the days for these years here. We can see now that we only extract the years from 61, and you can check that 60, 75, 76, etc. that had really low values here. We got rid of them, and now we can just apply a function here. So if we calculate this, this will be the mean daily precipitation, and if we multiply by the number of days per year, I'm gonna put .25 just to count for leap years. Then we have our mean annual precipitation in station 1115, which is this station here. Okay, this is its mean annual precipitation. So what we are going to do is just to loop this process for all the stations. Okay, basically we're gonna create the mean annual precipitation, and we just do the same, the group by oops, sorry, this is index year, and we apply the mean. So now we have the mean for every year for each station. I'm gonna just get rid of this because this is too big. Similarly, I'm just copy so we don't make any more mistakes. We copy this here, but instead of using it just in one station, we're gonna use it for the whole table. Good. And now we're gonna create a series where to save the data. The results. Okay, so let's gonna precipitation annual PD series, and index is going to be station index. Okay, so P and you can see that this, so it's basically the stations are the index. We're gonna fill in this table. So for each station in stations index, we're gonna do the same thing here. So this thing here, okay, we're gonna repeat it here. The only difference is that we have to add the station, and that's all. And then we have to save it in PN for that station. It will now plot PN. I made a mistake. Oh yeah, because this is not, we have to call here this, and now this is all done. Okay. The last thing is we're gonna add this series to stations. So station is our original data for the station, and we're gonna create here a new column with this mean annual precipitation. So let's call it PN and put it here, and our stations will have the annual precipitation here. Good. We can visualize the data now with a scatter plot. So let's plot elevation against mean annual precipitation. So this will be a scatter plot. This is the function in Matplotlib, and then we call the stations elevation to stations mean annual precipitation. This is our plot. Let's change a little bit the limits of the plot so we have a clearer idea. To define the limits in the y-axis, we use ylim, and then we have to set the minimum and the maximum. So let's use something like this. And then, as usual, let's give some labels to the axis y and an x. So this will be the elevation, mean mates about sea level. Label will be in millimeters. Semicolon here. Okay, we are plotting this to realize one thing. This is a physical fact that happens in most of the catchments. That so, the higher the altitude, the higher is the precipitation. It may not seem very significant, but you can see that there's a station almost at sea level with around 1,400 millimeters, but the stations are 500 meters above sea level are around 1,600 meters. So this is more or less a line, and we need to fit this line here. To do that, we're gonna use a linear regression, fit this linear regression in a way that better represents this point. So, good. Let's start with the linear regression. If we go here, just to explain it a little bit better. So this is our linear regression, this is our plot here, and we need to fit a regression like this one. So precipitation, annual precipitation, is a slope by the elevation plus an intercept. So I'm gonna go a little bit farther. Basically, we have an n, which is the value for elevation 0, and then a slope, which is the m. We need to fit those two parameters in this equation, m and n. Okay. To do that, we're going to import from SciPy stats. Let's import a function called linear regression. Okay. And to fit the linear regression, this is pretty easy. We get linear regress and shift tab to ask for the help. We need to introduce the values of x and y. So x is the elevation of the stations, and y is the mean annual precipitation of the stations. If we click, we get all these results. One is the slope, which is, we call it m, so let's put here m. Second is the intercept, that we call it here n, and then there are several performance metrics, and we're gonna save them as perform. With this asterisk here, we're just saving all these three values in one single object, which is called perf. Okay, so now we can see that we have a line with 0.49 slope and an intercept of 1410. This means that the line will start here in 1410, and then the slope will be this one here. The performance is quite interesting. The first value here is the coefficient of correlation, which has to be as close to 1 or -1 as possible. In our case, it's almost 0.75. This means that there's quite a strong correlation between elevation and p annual. And the second value is the p value. This has to be below 0.05 if we are very strict, and below 0.1 if we are not that strict. But if it's over 0.1, this means that there is not a significant relation between these two variables. Okay, but in our case, the coefficient of correlation is high enough and the p-value is low enough. So we can now plot the linear regression. We can copy this here, so copy, paste, and let's add to this the align with the linear regression. We can create a x limits array, which is going to be a numpy array. From 0 to, let's say, 2000 meters. And so let's plot this xlim, and then we multiply it by xlim plus n. So this is basically we can call it y here. Okay, let's call this x, and let's call this y. So y is basically applying the linear regression to x plus x. So this is the linear regression equation, and we can just plot here x against y and give it a style, so it will be dashed line in case for black color. So now we have our linear regression here. So why do we need this linear regression? Remember, we have something called weights, and for several elevations we have a weight. So we have to calculate what is the mean annual precipitation for each of these elevations. So we're gonna get with these values here, 50, get to the line, and out there to get the precipitation for each of these elevations. Okay, let's change it here, and estimate elevation for each elevation band. Okay. Remember that set bands was an array, a list like this. Okay, let's convert it to an array. This will be as simple as just passing here set bands. And if we want to calculate the p set in the original equation on the top of the exercise, we just do this: m by the elevations plus n. This is the equation of a linear regression. And then let's convert p set to a series, similar to what we did with the weights. Data p set, and index is going to be set bands. So p set is, I did something wrong. This is an array, and this is underscore. Okay, so now I have, similar to weights, a series with elevation bands and the interpolated precipitation for those elevation bands. So now we get to the last step of this exercise, which is calculate the areal precipitation. Okay. Remember here we are doing this here. So now we have an object, a series called weights, which are these values here, and another one called p set, which is this. So we just need to calculate now the summation of that product, and that is let's call it PRL, will be the summation of weights by p set, and this is our result. Good. Just one little thing more. Imagine I told you that there are plenty of ways to calculate this weights here. The simplest one will be the mean. What would have happened if we calculate P areal as the mean of the annual precipitation in all the stations? We would have gotten a different value, actually a much lower value. This is for one reason, because in this mean procedure we are not taking into account that the higher the elevation, the higher the precipitation, and most of the stations are usually, not just in this catchment, but in all the catchment around the world, in lower elevation, because they are just more accessible. So this is all for this exercise. Any question, I'm just glad to get any email or reply from Moodle. Thank you.